For our labs in velocity and acceleration, we'll be using a car and ramp setup. And the cars, whether you've got one of the plastic ones or one of these old wood ones like Paige is going to demonstrate with, all fit into the track a certain way. The wheels fit in the groove, and the car can be placed on the ramp and then released and let it coast down the ramp. Now in this case, the ramp is only in the fourth hole from the bottom, so it's not going to go very fast. Whether you have one of the newer plastic cars or one of the wooden cars like this one, you'll see that there's a little tab that sticks out the side. We'll call that a wing. And regardless of the type, that's exactly 5 centimeters, which would be 5/100ths of a meter. And the reason why that's an important distance is when this goes through the photogate, the leading edge will break the light beam and the car passes through, and when the back edge passes through the light beam, then it shuts off the timer. So you get a 5/100ths of a meter distance timed as it's going by the photogate. An important piece of equipment that we'll use for many of our labs in physics is a timing device that can be attached to photogates. Now this particular one is a CPO timer. It can be hooked to an external source of electricity through this port right here, and then there's an on-off switch also by where you hook it on, and I'll turn it on, and when you do, you'll get this display. And down here you can have it display in different timing modes. It just so happens that the one you most frequently use will be the interval mode. The other piece of equipment that goes with the timing device is a photogate. Photogate looks something like this, has a photo eye that shoots a beam of infrared light across. There's an indicator light that'll come on when we power it up. Has a thumb screw so that it can be attached and clamped onto tracks and other places where we will have objects move that we want to time. The photogate can be attached to the timer by means of a standard landline type telephone cord, and you'll notice that there's a little tab here that has to be depressed. You can squeeze that down like that, and where you hook it in, you'll notice that there is an asymmetrical port, and it just snaps right into place there. And then the other end of the cord then can be attached. I'm going to attach this one into the port, and again you'll notice they're asymmetrical, and the tab has to be depressed, and then you can put that into the A port. And when you do that now, you can reset that and you'll have 0 time showing. You'll also notice that when you do this, a little indicator light on the photogate itself comes on. Now this can be attached to any place on a track or anywhere that you want to time something, and what happens if you watch, I'll move my finger through the photogate, and that gives me a reading. 0.0868 seconds is how long it took me to move my finger through the photo eye. So I get a time from that position. I can reset that. The timing device is also set up so that you can hook a second photogate. Same procedure. Again, I'm going to use a different colored wire, and I believe yours will have 2 colors. I'm going to use B blue for my B photogate. Hook it up to the second port, and again depress a little tab and it'll snap into place, and I should be able to light both of these. Now when I do this, this enables me to time that passage as well as this passage, I can actually get 3 sets of time. I can get the time that it took to get through the A, the time that it took to get through the B, notice I just bring that light on, or the time between when I passed my finger through A and then later B. So depending on how many and which light is lit, it will tell me 3 different times from one experimental test. We now have all the apparatus assembled. We've got the car on the track is attached in the 4th hole, so we've got a slight incline. We've got photogate A, photogate B. We've measured the distance from photogate A to photogate B. That's an important number. We're going to want to know that when we find average velocity. We've got our timer set to interval mode, and if you need to adjust yours, that's what that button's for. You can set it on different types of timing. We want it on the interval mode. We want both photogate A and photogate B activated, and now we're ready to release the car. And the time that we have here, since both lights are lit, is the time that it took to get from A to B. 2.691 seconds was required for the car to get from the first photogate to the second photogate. That's the distance that we measured with our meter stick. Now, one of the nice things about our timer is if we shut off the B light, this 0.2841 seconds is how long it took that 5 centimeter wing on the car to go past point A. If we turn B on and shut A off, this time 0.2190 is the amount of time it took for that 5 centimeter wing to pass through photogate B. Now we have all the data that we need to calculate an instantaneous velocity at A, at B, and to find the average velocity from A to B. I'm going to use some of the data that we just collected from our demonstration run and work an example of the calculations for velocity. In our demonstration run, the time at photogate A was 0.2841 seconds. And I know the distance of my wing on the car was 500ths or 50 thousandths or 500 10,000ths. It's exactly a set amount. So I'm going to take that amount, the distance of the wing, and I'm going to divide that by the time from the photogate timer, and that'll give me a velocity of 0.1759. Now I'm going to round that to 3 significant figures, so I'm going to call that 0.176. Okay, now I'm going to go to my timer B, which read 0.2190. Now again, the wing on the car was 5 centimeters or 500 10,000ths. So I'm going to take that number and divide it by 0.2190, and that's going to give me the velocity at the photogate B, and again I'll round that off to 3 significant figures, 0.228. A faster velocity than what it was at A. This was further down the track. It was speeding up. This makes sense. On table 2, we want to find the average velocity from the measured values. You'll remember early on I put the meter stick and measured the difference between the two photo gates. And that distance in meters was 0.54. It was 54 and 4/10 centimeters, which is 0.544 meters. And then going back to my timer, the time from A to B was 2 seconds and 691 thousandths. So again, I have a distance between photo gates A and B and the time it took to get from photo gates A and B. So I'm going to take 0.544 and I'm going to divide that by 2.691, and that'll give me my average velocity down the track. And again, at 3 significant figures, that's going to be 0.202 meters per second. Now, one last thing I want to do, I want to confirm what I found from my average velocity here from table 2. And I'm just going to copy that down here. So I'm just going to bring that number down here. It says from table 2. I'm going to compare this average velocity from table 2 that we measured out with a calculated one. I'm going to go back to table 1 and I'm going to get my velocity at A, and I'm going to recopy that from velocity at A to velocity at A from table 1. So that was 0.176. Then velocity at B was 0.228. Now I'm going to add those together, 0.176 plus 0.228, and I get 404 for a total. And when I divide that by 2, because I combined two velocities, I got an average velocity of 0.202. So it matches up very nicely, matches perfectly what I had for my measured average velocity. I then can run each of my trials, raising the ramp by 1 hole and recording and calculating my data for each successive run as I did for this first one.